In this video, we'll look at a method that we can use to evaluate indefinite integrals or antiderivatives, and we'll do that by using substitution. We'll have to do this because a lot of the derivatives or a lot of the functions that we will want to find the antiderivative of will not be simple functions or will not be exactly the same as those that we defined. So what we'll have to do in those cases is substitute and make it look like one of the antiderivatives that we know. This is a good example here. It's a fairly complex function. We have the sine of x times e to the cosine of x. We do know how to take the antiderivative of sine of x, we know how to take the antiderivative of cosine of x, and we know how to take the antiderivative of the exponential function with e as the base. To simplify this, what we'll do is we'll look at that exponential function, and we'll replace that cosine of x with u. And so if we rewrite this, what we've got now is the integral of sine of x times e to the u with respect to x. Now that simplifies it to some extent, but not enough. One issue that we're going to have is that our variable of integration, as indicated by this dx here, this differential of x, is x, and if we start replacing things with u's, we want to get rid of the x's. So what we'll want to do here is we'll want to introduce the differential u. To do that, we're going to take the derivative of this, and we end up with du is equal to negative sine of x times dx. In this case here, when we take the derivative, we treat these differentials separately. We don't treat it as an entire derivative. We would get du over dx equals negative sine of x, and then solving for du, we get this. Now, this is convenient in this particular problem because we have sine of x dx in the problem. We have the sine of x dx here, and all we need to make a substitution here is a negative out front. Now, we can't just put a negative out front there without counteracting that, so we'll put a negative out in front of the integral also, and these two negatives here would bring us back to the positive that we started with. At this point now, we can replace the negative sine of x dx with du, and that simplifies this integral a lot. What we have now is the opposite of the integral of e to the u with respect to u, and that's one of the ones we know. We know that the integral of e to the u is e to the u, and so the opposite of that would be negative, or an opposite of e to the u plus our constant of integration. However, since we introduced this variable u, we need to get rid of it. We need to put it back in terms of x. So we'll replace the u with the cosine of x as we defined earlier, and we get our answer negative e to the cosine x plus c. What we're doing here, the substitution, is essentially accounting for the chain rule when we take the antiderivatives. If we were to take the derivative of this to confirm our answer, we would end up having to use the chain rule when we take the derivative of e to the cosine of x, and that's what gives us this integral right here. Looking at another example, at first glance this example does not look like an ideal example to use substitution, but if we rewrite the cotangent as cosine of x over sine of x, and again, it may not be immediately obvious which one we should substitute here, but if we replace the sine of x with u, and we replace cosine of x dx with du, because the derivative of sine of x is cosine of x, then we get a fairly simple equation here. And to evaluate this integral, we know that the integral of 1 over u with respect to u is the natural log of the absolute value of u. And we can't forget our constant of integration, and then just plugging in or substituting our x for u, we get the natural log of the absolute value of sine of x plus the constant of integration. Another example here. To simplify this, we will probably be best off replacing a 2x squared plus 1. This is an integral that we could evaluate by expanding this expression and writing it 2x squared plus 1 times 2x squared plus 1 times 2x squared plus 1, and writing it out as a long polynomial. But if we remember way back when we were doing derivatives and we introduced the chain rule, a lot of times that's going to be more work than is necessary. In this case, if u is equal to 2x squared plus 1, then du is going to equal 4x times dx. We don't have a 4x here, but we can take out a 5, and we end up getting the integral of 5u to the third with respect to u. And then we use our power rule. We increase the degree by 1 and then divide by that, and we get 5/4 u to the 4th power plus c. And so what we end up with then is 5/4 times the quantity 2x squared plus 1 to the 4th plus c.